Okay, it's 1:02, so we're going to go ahead and get started. Good afternoon. I'm Sam Moyer. I'm a research fellow here at the Emerging Technologies Institute at the National Defense Industrial Association, NDIA. Usually, Arun Serafin, our executive director, is host to our Tech 101s, but today that duty falls to me. I want to thank you all, as always, for your support of NDIA and for joining us for the webinar. Today's topic is Cloud Seeding 101 with Dr. Edward Jim Rice. The webinar is part of our Tech 101 series, where we present complex topics as introductory webinars with a focus on national security implications. This was once a niche topic, cloud seeding. It's now gaining attention as policymakers and defense leaders look for innovative ways to manage growing environmental risks. There's growing pressure from drought, shifting weather patterns, global instability tied to resource scarcity. Interest is now growing in how weather modification might contribute to long-term planning and operational stability. This introductory session will explore the evolving interest in cloud seeding, the strategic questions it raises, and its potential role in supporting both civilian infrastructure and defense preparedness. A couple administrative things before we get started. All attendee lines are muted. If you have questions during the webinar, please ask them in our Q&A box in the Zoom panel. And what we're going to do is address those questions after Jim has gone through his talk. We'll do our best to get through all the questions. We're recording today's webinar for members who are unable to attend, and we'll post that to our YouTube channel, as always, and our website. To quickly introduce our speaker, Jim is Senior Physical Scientist with the Government Accountability Office, GAO. He was a scientist and policy analyst for NOAA, National Oceanic and Atmospheric Administration. His last project was a survey investigating the plankton community of the waters around New York City. And Jim, thanks so much for being here. We're all looking forward to your talk.
Thanks very much, Sam. That last project was actually my PhD work from about 10 years ago.
Thanks for the clarification.
No problem. The most recent work, this ties nicely into the talk, actually, that I completed as a member of GAO, was a technology assessment on cloud seeding technology, which we published in December 19 of last year. You can find it online, and maybe we can put a link to it or something in the chat. But in the course of that work, we took a long look at historical examples, background on the technology, and then we looked at the current status of it, where it's being done, the benefits and the challenges, and what we call policy options, which could hopefully enhance or realize those benefits or address those challenges. So a lot of what you're going to see today is based off of that work and the background research that we did to that extent. So without further ado, I'm going to begin sharing my presentation. Let's see. Okay, here we go. And everyone should be able to see the slide.
Yes, sir, we can see it.
Okay. Let me minimize that. All right. Let me see if I can find. I'm gonna move some things around here. Sorry. All right, now we're in present mode. Okay. So as I mentioned at the beginning, this is the technology assessment that we did on cloud seeding technology. Here's a brief agenda of what I plan to cover in this webinar. It's, like I said, adapted from the assessment with a few tweaks here and there, reflecting what I know this audience is interested in, which is the defense applications, and a little bit more on the physical basis. There are a lot of technical terms that I'm going to, hopefully not too many, that I'm going to go through. So I will give you a brief overview. You're going to see the word cloud nuclei. That just means really small particles that can serve as the centering or starting point for a chain reaction that creates eventually a raindrop or an ice crystal and eventually snow. Other terms you might see is orographic, that just means mountains. Convective, that just means something big that's kind of circulating in the atmosphere. Those are the ones that come to mind as being maybe the most sort of technical so far. I try to keep this pretty at a pretty non-technical state. But so here's the bottom line up front. If you need to go away at some point, or you get tired of hearing my voice, as long as you remember this, you will have captured the essence of the talk. So the first is that cloud seeding is a technology that actually stretches back multiple decades. 70 years, in fact, is when the modern sort of cloud seeding technology that is still in use today was first developed and began to be applied. Throughout those 70 years, there's been peaks and valleys of government interest at the federal, state, and local level, as well as government support and oversight at those same levels. There's been boom years, there's been sort of bust years, and there's also been in some places a fairly consistent level. You'll see in a few minutes what I'm referring to. However, despite that long period of activity, there's also been some questions about its effectiveness even from the beginning. And to some extent, the effectiveness of cloud seeding technology is still fundamentally constrained by just the complexity and unpredictability of our atmosphere. Weather systems, even to this day, you can look outside, and if the air masses are relatively saturated, it can take a small change in temperature that may be hard to predict, and all of a sudden you've got a spring shower, right? Precipitation is still one of the harder things for scientists and for agencies, for my former employer, NOAA, to predict with the kind of accuracy that people would want. However, there are new technologies that have also been developed, over the past 70 years, and refinements of existing technologies that, if they were systematically applied and the data resulting from those applications was shared consistently and reliably, then we might be able to address some of that unpredictability that's inherently there and improve and get a better assessment of the effectiveness of cloud seeding technology. That's the bottom line up front. So if you want to tune out now, bye-bye. Thanks for sticking around. If not, let's go to the next slide. So why does this matter? This is from the introduction of our report. Governments around the world, including the US, currently spend billions of dollars attempting to mitigate the effects of drought, also the effects of too much rain, or some of the damage that comes from severe weather. So it is a topic that is always of interest. In fact, in 2022, Congress appropriated about $4 billion to mitigate the effects of drought in the Western US. And in 2023, the damages from drought totaled over 14 billion. Drought has long been a feature of the American West, stretching back not just tens to hundreds, but even thousands of years. There are long-term seasonal cycles, by which I mean like interdecadal patterns of drought that affect the Southwest. And then on top of that complexity, you also have short-term changes that are due on 2 to 3 year cycles driven by El Nino and La Nina. These are large-scale atmospheric patterns that recur on these multi-year cycles. And then on top of that, you also have climate change. You have increasing temperatures, especially hitting different parts of the globe in different ways. But within the West, you do have drought over time increasing. The challenge is that superimposed upon that trend is the complexity that exists on interdecadal timeframes and human choices. So increasing population, decreased recharge of aquifers and reservoirs. Lake Powell, which is the main reservoir from the Colorado River and the lower Colorado River states, which you can see here outlined in the hash marks. That's at its lowest level that it's been, I think, since it was even established. So it's a big challenge. And to address that challenge, communities, states, and local governments are looking at ways that they can improve their water resources, um, and turning to cloud seeding as a potentially a way to do that. As I said at the beginning, cloud seeding has been around for 70 years. It really relies on a breakthrough that occurred in the 1940s, um, which I'll discuss in a few more slides. But essentially, this breakthrough was addressing cloud physics, right? And that is the study of basically how clouds form, how they produce precipitation, their physical properties. The key thing to keep in mind is, clouds are basically water vapor condensed onto tiny nuclei, right? The water vapor needs something to adhere to and begin to grow around to form a raindrop that eventually falls out as precipitation. The droplets you currently see in a cloud, the puffy white, that's just very, 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 very tiny droplets that are so small that they're falling at a rate which is almost impossible to observe. And to get rain out of that cloud, those droplets need to become larger somehow. And so they can become larger basically by bumping into each other and sticking together. And they can become larger by attracting, more of the tiny droplets to one nuclei. So anything that can be used to accelerate that process could potentially be used to affect how precipitation is going to move out of that cloud. You could modify theoretically how quickly you make ordinary rain or how quickly you make snowfall, but also the processes that lead to hail formation, which can cause lots of damage. It's all a function of the distribution of these tiny droplets and their sizes. So too many small ones, you get very little precipitation. If you have a lot of big ones, then you can end up getting, in certain classes, you need to get the right conditions within the cloud, then you can get hail because you get that, runaway effect of a droplet becoming ice and then the ice getting larger and larger and larger before it falls out. So as I mentioned, the breakthrough in the 1940s that was achieved, these are the three individuals who were responsible for it: Vince Schaefer, Irving Langmuir, and Kurt Vonnegut's brother. I'm kind of blanking. The author, Kurt Vonnegut's brother. I'm kind of blanking on his name at the moment. Bernard, I think. Yeah, I think it was Bernard. So what they're doing there is they're looking into a cloud chamber, which is trying to recreate the conditions within a cloud. And the process they're observing is what happens if you add, in this instance, I think they first started with dry ice or CO2, and they introduced it and observed that if you cool down a part of the cloud rapidly, that you can cause the ice to spontaneously, form. They also observed that if you take a molecule that is similar in structure to ice, such as silver iodide, and do the same thing, that you can accelerate that process of nucleation and then building up an ice crystal into a snowflake or potentially into a raindrop. So that formed sort of the basis of what's called the chain of events, the physical chain of events that underlies cloud seeding. And it is the addition of glaciogenic seeding that's creating ice crystals, or hygroscopic seeding that's creating rain droplets, by adding in a seeding agent or stimulating the process of ice creation to more efficiently turn that water vapor into precipitation. So when this was discovered in the 1940s, it didn't take long before there were active programs in the West and actually across many parts of the US to see if they could stimulate rainfall, because drought has recurred in the US periodically since the founding, probably. But we had the Dust Bowl in the early part of the 20th century. And then recurring droughts, throughout our history. So there's always been interest in generating more rainfall. In the West, a lot of the rainfall throughout the spring comes from snowpack that's generated in the winter months. So here you see the approach used to generate that extra snowpack via cloud seeding. So these are orographic, as I said, mountain-based cloud systems. And in those instances, the mountains are effectively forcing an air mass that has water up. And as it's forced up, it goes into even colder temperatures. As the air mass cools, its ability to hold the moisture that's currently within that air mass goes down. And so the precipitation, the water within the cloud has to come out. So the ideal cloud in these systems is one that has, sufficient amount of supercooled liquid water, or which is the form of water that is there, ready to become precipitation, but it's missing enough nuclei to form the, the seed that's going to grow into a snowflake. And so what these operators will try to do is they'll either have ground-based generators that are going to be burning acetone and silver iodide mixes and sending off the seeding agent into winds that will carry that seeding agent up into the cloud base. Or they can also do it via aircraft and fly the aircraft to the right spot and do the same thing by burning flares attached to the underside of the wings. And often the more successful programs will do some combination of both of these approaches. If you look in states where they don't have mountains, but they still have drought and they want to generate more rainfall, they'll be looking instead at convective clouds. And the convective cloud, obviously it's harder to get at that cloud base because you can't simply climb up a mountain now to reach it. So they are all aircraft-based seeding programs, and they're looking for those updraft winds at the cloud base that are causing the towering, cumulonimbus clouds that we all associate with thunderstorms in the summer. And they're looking to introduce usually a salt particle, so the hygroscopic particles, calcium chloride is one that's often used, to cause the same sort of kickoff of the condensation, collision and coalescence that leads to the larger droplets that will fall out as increased rainfall. So there's lots of technologies that are used to try and create the extra rainfall, and not just used in terms of the seeding agent themselves, but there's a lot of supporting technologies these are where a lot of the advances have occurred since the 1940s. The seeding agents are fundamentally still the same by and large. The vast majority still tend to use silver iodide or calcium chloride or sodium chloride or other salts. Dry ice is used occasionally as well. Liquid propane is used for some ground generators because it tends to have an effect over a very small area, but the liquid propane basically cools down a chunk of the atmosphere so fast that the water will spontaneously form its own. Water droplets will form ice crystals themselves when they get to that temperature, and then that'll serve as the nucleating agent to create a snowflake. So a lot of ski resorts will use potentially liquid propane just based on where they need more snow to make the runs open. So the seeding agents, those are the main ones. The purpose, as I said, is to promote the formation of ice crystals or water droplets. The emerging technologies that are basically in the development stage, some researchers are looking at sort of biological seeding agents, which are based on a common bacteria that occurs, across the world, Pseudomonas, and has been found, in rainfall and found in snow. And the theory is that the outer shell of this bacterium, for whatever reason, can serve potentially as a good nucleating agent because it can be very stable and you don't have to keep it super cool like you do with liquid propane, which just lowers your cost, right? If it's potentially a good seeding agent. Other researchers are looking at electrically charging water itself, so that it attracts, other water droplets more rapidly when it's released. And then engineered nanomaterials. So these are essentially titanium dioxide is one of them. It's being developed in the Middle East. There's a lot of countries in the Middle East that are very interested in cloud seeding for obvious reasons. They don't have a lot of water to begin with, and their ground reservoirs have been going down over time significantly. So that's on the forefront. The other key technology for cloud seeding is the delivery mechanism. How do you get the seeding agent, to where it needs to be within the cloud? You can't simply just, shoot it anywhere into the cloud. It needs to go to the right spot. And that requires, as you saw in the earlier graphic, either having an aircraft that is actively looking at the cloud conditions to find that right spot, flying to it and releasing the flares, or you have a ground generator and you've hopefully put it in the right spot where it's going to release that into the upwinds that'll carry the agent into the base of the cloud. Other technologies that are used outside of the US, artillery is used in China and I believe Russia, as well as rockets. So obviously then you're just shooting that artillery round into where you want the cloud seeding agent to go. The technologies that are in development are UAS and balloons have been around a long time, but balloons specifically for the delivery of cloud seeding agent is something that's still on the emerging front. The big limitation with UAS is that they have an altitude restriction, and FAA rules mean you have to keep sight of your UAS at all times. Obviously, if you need to fly it into a cloud, that's a problem because you can't see it anymore. There's been limited waivers granted for the use of UAS, but they do exist. And the other limitation on them too is the payload. They just can't carry as much as a full manned aircraft can. The other category for technologies that are really relevant for UAS, and this is probably where the most advancement has happened in the past 70 years, has been in the field of real-time sensors, by which I'm referring to, radar, LiDAR, which is light detection and ranging, basically using wavelengths of light as opposed to radio waves to measure the distance to things and get information on its movement. And then radiometers. The radiometers are really key, but really expensive. And in situ probes are also key, and those are things you can mount on an aircraft or things you could mount on a UAS, which will let you measure the characteristics of that cloud and the water within it directly. So the key focus there is as I mentioned, you need to know the distribution of the size of the droplets in the spot you want to seed in so that you can know if your seeding agent is going to be maximally effective. So that's the direction that the community, the researchers, and some of the larger operators want to go to, is ever more precise information about the cloud conditions to let them tailor their seeding agent delivery to get the biggest impact for what they're doing. So that's why they want to miniaturize them, and they want to put them on UAS, or they also want to look at adapting remote sensing data from satellite systems or portable radar systems you can move around to get at that information they need. The other categories, models and software. The idea behind the models and software is to plan your operations with better efficiency and more effectiveness, but also to get a better sense of the effect that your operation had. And that requires, I'll get to this when I talk about the fundamental limitation, but you need to know what would have happened if you hadn't seeded to know how effective your seeding operation was. And that's because you're picking clouds that have a lot of water moisture that is, for whatever reason, not precipitating out. That's your target cloud, right? So having good forecast information, so you know where the cloud system is going, how likely it is to hit conditions where the precipitation is going to come out, um, and then having models that will let you evaluate, well, what would have happened if I hadn't seeded, to get a sense of what was the effect overall of the seeding effort, and then combining those with models for, well, what happens after that rain hits the ground? Did I end up seeding in the right spot so that, all that extra precipitation is going to flow into the aquifer that, I'm being paid to recharge? Or is it just going to end up on a parking lot, and potentially evaporating away, right? Or never reaching, the reservoir I want it to? Those are big questions when it comes to effectiveness overall, and it's still, an emerging area of research to try and tie those two models together. And as you can imagine, key to all of that also is being able to accurately measure, well, what did fall? How much snow fell? How much rain fell? Um, what was the precipitation on the ground surface? And so moving the last category, experimental facilities, you can think about it this way. Those are all of the assessment effectiveness from the precipitation perspective. The experimental facilities are trying to get at the physics of what's happening in the cloud, and looking at the effectiveness, of the seeding agent in terms of kicking off that condensation, coalescence and process that leads to enhanced precipitation. So they're trying to simulate, well, what will happen when I add my seeding agent? The current use of, we don't have many cloud chambers in the US anymore. We have maybe two, and they're not that big compared to cloud chambers in other countries. Big isn't necessarily better, either. You need the right mix of instrumentation within the chamber. But other countries such as Germany and the UK have more advanced cloud chambers, and China has a very large cloud chamber as well. China has probably the largest cloud seeding program that's sponsored and run by government agencies in the world. So it should be no surprise that they'd also have the biggest cloud chamber. If you wanted, so this is a picture of what's actually probably the most commonly used technology. That's a ground generator on the right, actively burning, the acetone and silver iodide mixture. This is from Lake Tahoe, where my team and I visited a program that runs, based out of Nevada, that runs these generators to try and ensure there's adequate water being deposited into the reservoirs that are to the east of Lake Tahoe. So these generators are basically targeting the marine clouds that come in laden with moisture off the Pacific, but in some cases aren't, don't end up producing as much snow or rainfall as the residents would like. So they fund this effort to increase snowfall so they have more water in the spring. That's the big benefit of cloud seeding is, if it's done effectively, then communities can have a more reliable water supply for cities, for farms, for industry. There are several industries that use a lot of water as part of their manufacturing processes. Environmental conditions can potentially also be improved. You can reduce the risk of wildfires if you can increase the moisture content in vegetation and reduce the drying out and creation of tinder. You can also improve habitat and natural resources for whatever species are at risk or endangered. And then there's health benefits. This is a big reason that cloud seeding is touted as effective in China and India, reducing air pollution by basically causing it to rain out, all the particulates that may be floating around in the atmosphere as smog. And then there's direct economic benefits. So aside from like getting more rain for crops, right? Hail damage can be very expensive for farmers, and it can also be very expensive for private individuals, companies, municipalities, because if you've ever seen a hailstone, they can cause a lot of damage when they hit things. So anything that can reduce the size of those hailstones or potentially inhibit them altogether is economically viable or valuable. Um, for communities that are looking at ways to boost their water supply, there are expensive options. In some cases, even buying the water is viewed as more expensive than trying to generate the water via cloud seeding. And it's the most expensive option in many cases is to try and treat your wastewater with filtration systems uh, like a water filtration plant, for example, can be very expensive, on the order of like tens of millions of dollars to build one. Um, Also, recreationally, if your ski slopes are not able to be open because they didn't have enough snow, that can cause an economic hit to communities that rely on it, and the same with communities that rely on whitewater rafting or kayaking. So turning to defense, when we talked to DoD in the course of our work on the technology assessment, they assured us that there are no current active weather modification programs, either in research or operations at DoD. However, in the course of our research, we came across historical programs that have been used by DoD or other government agencies. Probably one of the more famous or infamous, depending on your perspective, is Operation Popeye, which occurred during the Vietnam era. And in Popeye, the intent, the idea was to actually use cloud seeding. The Air Force adapted um, some of its aircraft, I think it was C-130s, WC-130s, to basically become cloud seeding aircraft. And they targeted monsoon clouds coming into Vietnam with silver iodide to increase rainfall and basically flood out supply lines that were being used in Laos and northern Vietnam to reach southern Vietnam irregular forces, the Viet Cong. So the idea was to basically disrupt their logistics by just making the roads they were using untenable. At the time, while the program was ongoing, the analysis was indicating that it was effective, that they were causing an increase in rainfall. However, years later, and towards the end of the program, they started to realize it wasn't really having an effect, and what they were actually seeing was just normal rainfall patterns. And that caused the program to be canceled. It was costing at the time in the tens of millions of dollars. So in DoD, world, that's not a lot of money, but it wasn't viewed as a worthwhile investment at the end of the day, so they canceled it. One of the other investments that has actually been adapted in some cases by states is you could use cloud seeding to reduce fog. Fog is essentially a cloud, on the ground. So if you were able to introduce enough of the right size of, seeding agent into fog, you can cause all of that precipitation to rain out. The problem is that you haven't altered the fundamental meteorological conditions that led to the creation of that fog. So unless you do it again very quickly, um, then the fog's just going to come right back. So it's something that does need to be repeated if you want to cause a longer effect. However, that may be exactly the window of time that someone is looking for operationally. If you need to open up a runway and it needs to be open for 15 minutes or 20 minutes to let aircraft come in that otherwise couldn't land there, then that could be a worthwhile investment. The same could apply if you're transporting supplies along coastal highways and a coastal fog comes in and all the traffic needs to stop. If you can give yourself a window of 2 hours when traffic can move again, that might be viewed as worth it. So far, we've found only one state that's tried that, and a single airport in Oregon, but historically that's been investigated as well. And then, as I mentioned, the other application is just reducing the damage to infrastructure. DoD has lots of expensive systems that need to be outdoors. I'm thinking radar, antennas. If you can reduce the damage to those systems from hail, then that could also be a worthwhile application. But as I said, there's fundamental challenges to cloud seeding. The biggest are that baseline precipitation, knowing what would have happened if I hadn't conducted cloud seeding operations. And then also, because of the inherent unpredictability of the atmosphere, you either need very, very good models or you need lots of observations to establish whether or not you had a statistically significant effect, because the variation is so huge, right? So you need a lot of data to constrain that variation and determine, well, if I know that the max effect I might have is 20%, then you're going to need to really get a lot of obs, to determine whether or not, if the precipitation variation naturally is 30%, then I need to get even more observations, right? So one study we found, they noted that the average increase in precipitation across 118 randomized cases, this is for an orographic cloud seeding scenario, was 3%. But the variation on that number was so large that the effect was indistinguishable from zero. So that's the best case scenario, is the orographic systems, lots of observations. The other uncertainty is, and fundamental challenge is, say you've estimated that you generated 5% reliably coming out of the cloud, but how much of that reached the ground and how much of that reached where you wanted it to go? Because rain that falls, where it becomes inaccessible or unusable water is not really effective for water supplies. You need it to go into the reservoir that you're going to use. And that is very hard to get a sense of, right? Because water can evaporate if it doesn't fall in the right spot. You may not have a good model of what the land surface is going to do to the water flow. Vegetation could be a big factor as well. And that's all basically a fundamental challenge that is still unresolved. And then the technical challenges. What you see here is a radar coverage map for the Western US, which is where most of the cloud seeding programs are. And as you can see, there are gaps where there is effectively no radar coverage at levels that would be good to have for cloud seeding operations. And this is due to, the curvature of the Earth in some cases, but mainly the beam blockage from terrain. And as I said, radar is the primary tool that's used. So this is a big challenge to cloud seeding. Non-technical challenges, environmental health effects. We found that there's relatively good agreement that at the current levels, silver iodide does not appear to present a significant human health or environmental threat, because silver iodide is largely insoluble in water. It can dissolve, but it takes a very long time or specific conditions for the silver iodide to release the silver ions. The silver ions themselves, that's what is really responsible for potential harm. It's a very antimicrobial substance. But we don't know exactly what would happen if you were to massively scale up cloud seeding and start, putting silver iodide in a lot more places and at a lot higher doses. That hasn't been researched recently at all. So that's an unknown. The other unknown is the downstream effects. So say you cause a small increase in precipitation in your target area, but you used a lot of material to cause that. Some of that material may continue to move with the wind, into another area. What would be the effect in that other area? And research that we reviewed has shown it could go either way. In some cases, it may cause a small increase, and in other cases, it appears to cause a small decrease in precipitation. So that's also something that needs to be studied more extensively to get a good sense of how common that is, how much to expect it. So as I said, this is the conclusion. So, cloud seeding has been done since the 40s. The advances in radars and sensor technology, they hold the promise of potentially improving precision to get a better sense of effectiveness. We identified 5 policy options to help, move in that direction in our TA, improving the infrastructure, doing some more targeted research, and really improving the coordination between stakeholders within the cloud seeding community to include the agencies that provide oversight. And at that, I will stop presenting and take any questions.
Outstanding. That was very enlightening, Jim. We've had some great questions rolling in. So let me get to a couple of them. So we've had a number of questions about future trends and what we might predict about where this technology might go. Um, a couple questions about different kinds of technology and how they might apply. You talked about UAVs. We also had questions about the potential for AI to improve targeting or
Hmm.
to or for other use cases. Um, Physics-based models are expected to continue to improve, and of course, sensors. You mentioned um, radar and lidar. So, out of all of those, are any of those expected to significantly change the efficacy of cloud seeding in the future? And if so, how?
Wow, it's a great. So significantly, I think it's not going to be in any of those scenarios. I think it's going to be probably more of an all of the above. And I also don't want to undermine the non-technical challenges. What we found in our work was that there are some agencies out there, or there are some private sector operators that are using the latest technology that are basically squeezing every last ounce of efficiency that they can out of the technology. But their fundamental limitation, tends to be um, the infrastructure of radar and then measurement of precipitation that reaches the ground. Uh, the other big limitation is on the modeling. So the the driver for there's one model that exists for um, linking, our national level model for the weather in the United States with a cloud seeding cloud physics model. It's called WRF Weather Mod, WRF dash Weather Mod, Weather Research and Forecasting Model, Weather Modification. A lot of the people we talked to said this could be a game changer, but it's not widely used and people don't understand it. The operators don't necessarily understand it. So a lot of operators, they're just using their tried and true techniques that have not changed in many ways from what was done in the 1970s. And some of them are leaning into the technology. I think if we're going to see in a really effective, an increase in effectiveness, we're going to need to see the community moving towards a more standard approach to assessing effectiveness and to planning their operations. There's existing technologies on the table that can help with that. The problem is a lot of them are too expensive for these smaller operators to use. A lot of state agencies don't require evaluations of the work. And I think AI is potentially helpful, but with AI, I mean, you really need to have someone knowledgeable curating the data that goes in to train that model. Um, and I think meteorology is potentially well suited to that because NOAA has a big database. They've been moving towards, AI for a while. They're not quite there yet. I worked on a TA on AI and environmental models actually prior to the cloud seeding one. And that was one of our big observations is that AI has potential to transform meteorology, but there's still some significant hurdles when it comes to curating the data, making it accessible, making it AI ready. So I don't think we're necessarily there yet with AI. And I think a lot of um, the gains could be realized by addressing these non-technical issues and improving the infrastructure for radar coverage and precipitation.
That's great. And some of our questions when they asked about AI and related technologies, they were curious about targeting specifically. Is that an area of particular promise where you think the technology is relevant? Is targeting something where there is an expectation that's something that could be improved in a significant way, or are there other margins that are being looked at instead?
Targeting, you mean targeting like within the cloud where to seed or targeting the precipitation
Exactly.
that comes out? Okay. Yeah, I think that's the fundamental challenge that these operations have is being able to target the right spot of the cloud. AI could be really helpful if you're able to get a large enough database that is taking, say, a very easy to get uh, type of information about a cloud, say just the radar returns from NexRad. And then if AI can be paired with another data set that has the specific cloud seeding relevant data, so the droplet distribution, And the AI is able to learn the association between those two data sets, because that's what AI does best. It's, the world's best like regression and analysis engine, right? It'll give you a formula for linking X and Y. Just don't pay too much attention to that formula and how it works. If it works, it works. AI is great at that, so potentially could help with targeting if the data sets existed and could be trained, to come up with that formula, that algorithm that says, if you're seeing this on, your cheap radar, this is what the droplet distribution is most likely to be. Now is the time to, or here's the place to introduce your seeding agent. So could be, but it's the same challenge of you need the data set and you need someone knowledgeable to build the algorithm that can link those two things.
Excellent. We also have two good questions that touch on legal and regulatory issues. One question asks about how serious the regulatory or permitting requirements are here, and whether those are a significant obstacle. And another question mentions a long-standing lawsuit between Colorado and Utah, in which Colorado was claiming that Utah was stealing their water, as Utah had a coordinated program for cloud seeding. So curious
Colorado
if
does
you.
too. But yeah, that legal case came up in our research. Sorry, go ahead.
Well, so over to you. Curious if you view those as significant obstacles, and are those potential areas that could be addressed that might speed up the technology deployment?
So yeah, there's a patchwork of laws. If you look in our report, I think it's our first table maybe that we have, where we summarize like all of the different types of oversight that happen in the West. And in some places, a license is required. In other cases, you need to get a specific permit for your activity. So it's not like you just get the license and you can do it, whenever or wherever, as long as you follow the NOAA regulations. So currently, we only have one overarching federal requirement for cloud seeding, and it is strictly a reporting requirement. It's a 2-page form. Really, it's 1 page. It's just 1 page that in which you specify, here's where I'm going to go, here's what I'm going to use, here's the time duration, and then you indicate, whether or not you have consulted or done an environmental assessment, whether or not you've looked at forecast information, and whether or not you have a safety plan. And that's it. And then there's an interim that's also like 1 page, which could also be the final. So it's very lax kind of federal level oversight. Most of the real oversight exists at the state level. But at the state level, there's also wide variance. Texas, for example, their program was described to us as being kind of minimal. They basically just give a license to somebody who's, got a reasonable track record of doing cloud seeding, and then annually there may be, an assessment, but that's all done at the association level. Other states will have evaluations required as part of the permitting process. They'll require regular updates, as the project goes on, and they'll require the person to show that they have training in the field and certification in the field to perform the operation. The question of whether or not it makes sense to have everybody at the same level or everybody at a lower level, that's something in our TA, which we said, that's something that the states need to work out, and the stakeholders need to work out, because there are instances in which it may make sense for one state to have higher thresholds for permitting and another state to have lower ones. But having this patchwork is also not ideal either, because it makes operators operate in totally different ways depending on which state they're in. And that can lead to inefficiencies, in the marketplace. But that's a good question, and it's something that we do address in the TA. One thing we do say would be probably better to consider is having an evaluation component be part of the permitting. We came across in our work anecdotal evidence of operators following the contract to the letter of the law, for example, and the contract was written by the state or a water district, and it just said you have to spray X amount of seeding agent, for this month. Okay, so they would literally park the ground generator in the parking lot of a Walmart and just spray the agent at the end of the month. They were nowhere near the mountain range or the conditions that would lead to the agent actually going up, seeding agent going up and potentially causing cloud seeding to take off. But that's the cost of having a patchwork of loose and high restrictions, is that you also enable some operators to get by with doing things that are just never going to work. So that for that reason, we said maybe you should think about an evaluation component being part of this, so that people who don't do it the right way, even following the standard of practice, won't necessarily keep taking money from taxpayers.
Got it. That's really interesting context. So a number of other good questions and some interesting comments here as well from folks who sounds like are pretty informed about the topic. So thanks for adding those into the discussion. In terms of questions rather, you already addressed this, Jim, but in terms of safety effects, number of questions about that, questions about specific chemicals. So I believe that you called out silver iodide specifically. You also mentioned acetone, calcium chloride. So any other comments you would add for folks who are interested in safety effects that weren't already addressed before?
Yeah, there's as I said, there hasn't been, we didn't find a huge amount of research into the negative environmental impacts of the most common cloud seeding agent, silver iodide. That's the one we focused on because it's the one used by and large mostly across the US. There are other kinds that are used abroad in other countries, but they also still, I think the plurality of them tends to be silver iodide. But the most interesting, potential effect that we saw reported was if you have a lot of silver iodide building up, in an ecosystem, that it can, begin to interact with other environmental stressors, and then you can end up with a net effect that can, inhibit certain organisms, especially ones that are lower down on the food chain. So, like bacteria, different types of worms, they can experience the effects first. It can take a long time potentially to see those effects too, because it takes a while, for that level to build up to a critical threshold. But it would be, I think, interesting to it would be good to have more research done in this area, because as we know, there are countries that have been, like in China, they have been doing cloud seeding for decades at a really big scale. And I don't think there's a really good picture of what the environmental effects, are potentially going to be from that. As far as the other emerging technologies, that would also be interesting. Especially the titanium dioxide. The good thing is, if an operator is introducing a new seeding agent or is fundamentally changing the way seeding is done, then they would have to go back to EPA and apply, to do it. Currently, the existing conventional technologies and conventional seeding agents were grandfathered in to TSCA, the Toxic Substances Control Act, because they predated it. And so EPA says, well, as long as you're still using the same thing in roughly the same way, you're not going to need to apply underneath TSCA, for a permit to use it. But new agents will, right? So we'll just have to see, what the results of that are. Yeah.
Okay, we're coming short on time, so I'm going to ask one more question, and thank everybody for your participation, and then I'll provide some closing remarks. So last question will be about resourcing. We had a question about respective size of different funders, things like venture capitalists versus private companies versus state governments, federal governments. You mentioned China having, sounds like, the world's largest program here. Would you be able to provide a general sense of the size of those funding, how they compare, and did anybody you talked to indicate that there's a need or opportunity potentially for more funding in this space, that more could be done with more funding or needs to be done?
Yeah, let me look at our report really quickly, because we did actually find some evidence that talked about China's level of funding, which take it with a grain of salt. Um, not entirely sure what that how reliable that number may be.
And while Jim is pulling that up, I'll just reiterate that this presentation will be posted on YouTube shortly, and it'll include links to the resources we discussed, including, of course, his GAO paper that provides the deep dive to all this.
Okay. 6 measurements of China. Okay. So China has the largest weather modification program. It's reportedly $2 billion in total spent between 2014 and 2021. One of the other big funders is Saudi Arabia. They have spent over $256 million in 2022 alone in support of the first year of their regional cloud seeding program. And the UAE is spending about giving out about $22.5 million in grant, have given out $22.5 million in grants since 2016. India is also recently approved $4.36 million for cloud seeding to address drought. Utah just approved about $12 million for their program. So that's, but other places, in Texas, there's no money given by the state. All the money comes from the local water districts. Texas just gives a stamp on your license that says you're good. So it really varies. It really varies quite a bit. At the heyday of U.S. federal support, I believe it was like 78 million in 2024 dollars, around that level. That was provided about 40 years ago to cloud seeding programs, but those all ended. Those big programs ended in the 1980s, and they haven't restarted. So venture capital is interested in this space. Can't say much more than that. It relates to ongoing work. You can go online, though, and find examples. A lot of that venture capital interest is also in something called geoengineering, which we scoped out of our report. That's trying to alter basically climate processes via cloud seeding, which you can fundamentally use the same approach to do. You're just trying to achieve a different effect. We had more than enough on our plate just looking at cloud seeding in that TA. But there are other reports from GAO on geoengineering. If you want to look for them, you can find them. Just type those words in to Google.
Outstanding. Well, thank you, Jim. We have to close out now, so we'll just pull up a couple quick slides to thank you for your attendance. Thanks to Jim. If you have feedback about this event, please email us at eti@ndia.org. And we have a couple upcoming events that we'd like to highlight for you. We've got another 101 coming up in June, and we have some other webinars coming up as well in May that we should highlight for you. One of them is Navigating Uncertainty, that's simulation as a tool for policy innovation. That's on 22 May. And then we've got one coming up on quantum supply chain vulnerabilities with Dr. Carl Williams. That's going to be a really exciting one. And that's on 28 May. And look out at our NDI events page for updates on all of these events. And lastly, of course, we have our annual conference at the DC Convention Center. That's the NDIA Tech Expo. That is in late August. So if you want to learn about NDIA and all of our ongoing activities, divisions, please visit ndia.org. Thanks again for your attendance today.